Hi everybody. So the next section we want to look at is section 2.2 on limits of a function and limit laws. So this is kind of where we're going to start to introduce more of the ideas of calculus and how to deal with this idea of closeness, or what it means for two things to get closer together. And I should mention that there are other approaches to this, but we won't be talking about them. This is sort of the more standard approach using limits. So let's define what a limit of a function is. So remember, a function is a curve that passes the vertical line test, right? So the limit of a function relates, again, like I said, to this idea of closeness, and it's written this way. You can sort of interpret this as saying that as x gets closer to a, so remember, this is sort of the height of the function. So we're saying as x gets closer and closer to some number a, the height of the function basically gets closer and closer to this value L, right? So you can kind of think of it this way, right? You've got a function here. Here's your x and y axis, and let's say that this is a on the x-axis, and you're saying, you're moving along the curve, and as x gets closer to a, as you're moving this way, right? You're basically saying that the height of the function will get closer to this height L. One thing to mention here is the limit of a function does not have to actually equal the value of L at the point. It just has to get closer there. So it may be that the function is even undefined at L, right? What we're looking at is what is the behavior as we get closer and closer to A? What does it look like the height of the function is approaching? So here's an example. If you look at the function x squared minus 1 over x minus 1, that gives you this function. Now the function isn't defined at 1 because 1 is not in the domain. If you simplify this, you'll notice you can factor the top and then cancel out the x minus 1s, which gives you x plus 1. So this function is almost the same thing as the function y equals x plus 1, except the function y equals x plus 1 is defined at 1, right? So when x is 1, y is 2. So these functions are almost the same, but not quite. But they do have the same limit as x approaches 1, right? So as x approaches 1 here, it looks like the height of the function is getting closer and closer to 2, even though it's not defined at x is equal to 1. Same thing here, right? Even though it's defined there, the height of the function will get closer and closer to 2. So if we pick some values of x, and I guess x doesn't have to get closer from the left, it can also get closer from the right-hand side as well. But you'll notice as we pick values for x closer and closer to 1 from the right and left-hand side, right, the height of the function does look like it's getting closer to 2, right? So these are the values of x that we're picking. 0.9, so a point to the left, and then a point to the right, 1.1, another point to the left, and another point to the right that's closer. And so as we do that, it looks like the height of this function is approaching 2, which is what this function would approach. And these two functions are equal everywhere except that x is equal to 1, where this function is undefined. So we'll see that these functions, even though they're all slightly different, all have the same limit, right? And this function in particular might be kind of weird because we're saying the height of the function at x when x is 1, not 2. And you might say, well, it's not actually approaching the height of the function, but that's okay, right? It basically, for the limit to exist, it just has to approach the same height from the left and the right. It doesn't actually have to reach that height, right? So you can think of there's a sort of a cloud or a mist around here, and as long as it looks like you're getting closer and closer to that height as you move from the left and the right, then that is the limit of the function at that point. So if you have a function that's continuous like this, either it doesn't have to be a straight line, but maybe a curved line or a straight line like this or straight line like this, right? These functions will be have limits at every value of x, right? In fact, these will also, right? Because you can find the limit here and here even at the point where it's undefined. Now there will be some functions where maybe that's not the case. So let's look at an example to kind of clarify this. So here we have some function, right? There's no rule for it. We don't have an equation for it or anything. But let's ask ourselves, what are the limits as we approach various values? So let's say I'm asking, this is saying what height is the function approaching as t gets closer to -2. And here I have the t-axis instead of the x-axis. So as x is getting closer and closer to -2, what height does it look like the function is getting closer to? Now the function itself is undefined there, but it looks like it's getting closer and closer to height 0, so the limit of this would be 0, right? What's the limit as x approaches -1? Well, as I approach -1 from the left and the right, it looks like the height of that function is approaching -1, so that would be -1. Right? What about when x is getting closer to 0, or t is getting closer to 0? So as I get closer to 0 from the left and the right, unfortunately they don't approach the same height, right? So this approaches height -1, this approaches height 1. In fact, the function itself is defined to be 0 here, right? So you might be tempted to say, well, the limit is 0 because that's the actual height of the function. But remember, we're looking at what height does it look like the function is approaching as you get closer and closer. Well, in this case, it looks like you're approaching 1 from the left and -1 from the right, so that doesn't seem to make sense. So we'll just say that that limit does not exist. If you look at, say, -0.5 from the left and the right, so here x or t is approaching -0.5, it looks like that would also be height -1. Now you can have functions without limits as well. I guess we looked at this example, right? This didn't really have a limit as t approached 0. So if you have a like a jump discontinuity here, this function would not have a limit as you approach 1. I guess it'd have a limit everywhere else, right? Any other point here, the limit of any point on the x-axis here would have a height of 1. The limit of any point over here would have a height of 0. Here's an example of a function that doesn't have a limit. So as you approach 0 from the left, it looks like the function goes up to height infinity. And if you approach 0 from the right, if you approach 0 from the left, you also go down to height -infinity. And so that doesn't have a limit there. And then you can also have something like this, where, again, this function is kind of hard to graph because of the 1 over x. It's basically the graph of sine, except the the wiggling here gets compressed between 1 and -1. And the idea is that as you approach 0 here, the oscillations are so rapid that it doesn't actually settle down to a particular height here. You might think it approaches height 0, but it just keeps oscillating more and more wildly. So here's an example of a function that you can't even graph with a graphing calculator. No matter how much you zoom in here, it's still going to look crazy. So again, in a lot of cases, graphing calculators will help you, but in some cases, you might need to do sort of a more of an intuitive analysis. But so these are all examples of functions that do not have limits, and this function is even continuous right up until we get to this point, but it still doesn't have a limit. So that brings us to the limit rules, which is if you have two different functions and you take the limit as x approaches c, and the limit of some other function g of x as x approaches c. Let's say that the height of g approaches m, and the height of L or f of x approaches L as x gets closer to c. It turns out that these the limits satisfy very simple rules, namely, if you're asking what's the height as x approaches c as of f of x plus g of x, well, that's just the product of the two limits together, right? I mean, so if you add two functions, if you have some function f of x and some other function g of x, you can just add the two heights together, and that would give you some other function f plus g of x. And it just turns out that the limit, say at this point c, is basically the height of f of x at that point plus the height of g of x at that point. Subtraction is the same. If you take a constant times a function, you can just pull that constant out. So let's say you're asking what's the limit as, say, x approaches, say, 2 of 3x squared. Well, and again, this might seem kind of silly, but you could actually pull that 3 out, in other words, and then take the limit of x as x approaches, of x squared as x approaches 2. So that would be like 3 times 4, which would be 12, right? If you have two functions that are being multiplied together, you can multiply their limits. And again, in this case, remember that f of x and g of x have to be approaching the same value c, right? So you couldn't do this if, like, say, x was approaching 2 for f of x and x was approaching 5 for g of x. Right? If you're dividing two functions, again, you can just basically plug the value c in for these, provided the bottom function is not 0. If you have a function raised to a power, you can basically, what this rule is saying is you can take the, you can apply the power to the whole thing and put the limit inside the power. If you have a nth root, a cube root, square root, fifth root, eighth root, whatever. Again, this is basically saying that you can take the limit, you know, inside the root sign. So we'll look at some examples of these here in just a minute. But one important theorem here is that if you have a polynomial function, right? Remember, a polynomial function is just something in the form like, say, 5x to the 7th minus 2x to the 5th plus, say, 4x to the 4th minus x cubed plus x squared plus 7. Notice some of the coefficients could be 0, right? There's no x to the 6th term or constant term there. And if you want to take the limit of that as, say, x approaches 1, what this is basically saying is you can just stick 1 in for all the x's, right? So this would be really easy to evaluate. It would just be, you know, 5 times 1 to the 7th minus 2 times 1 to the 5th plus 4 times 1 to the 4th minus 1 cubed. And you know, you don't necessarily have to write down all these steps. I mean, you can probably do this in your head. You know, 1 to any power is just 1, so this is just going to be 5 minus 2 plus 4 minus 1 plus 1 plus 7, right? Whatever that gives you. So collecting all the positive terms, 5 plus 4 is 9, plus, so they'll give you, what, 17 minus 3, so that'll give you, what, 14. So basically what this says is if you have a polynomial function, you know, you technically should use all these rules. And, you know, my professor was really picky about this. You know, technically you should really, you know, break the limit up first. You should, you know, you should take the limit as x approaches 1 of each term here, you know, minus the limit as x approaches 1 of 2x to the 5th. But I'm not going to have you do that, right? And then you tap the limit as x approaches 1 of 4x to the 4th. And then technically you'd have to take the 5 out front, right? Because that would be a constant. So I'm basically using this rule. You know, if you have a bunch of things added or subtracted together, you can just take the limit of each thing separately. And then I can pull the constants out front, like I can pull the 5 out front and the 2 out front. And then because these are x's raised to a power, you know, if I have x to the 7th, I can just, you know, I could write this as the limit 5 times the limit of x to the 7th. But, you know, that's kind of tedious. So if it's a polynomial, this theorem basically just allows you to plug in here. But this theorem is basically a consequence of all these rules. Okay. Now, if it's not a polynomial function, if it's a rational function or a sine function or a trig function, right, this rule may not apply, but we'll see in a lot of cases you can simply just stick the limit in there, right? Because we're basically asking, you know, as x approaches 1, what height does this function approach? It's, you know, it's basically kind of like making an x-y table, right? When x is 1, what's y, right? Now, you got to be a little bit careful about that, especially when you're dealing with more complicated functions. But essentially, we'll see that that's largely what you can do. So if you have some polynomial function like this, again, you know, the long way to do this would be to take the limit of each term separately, and then pull the 3 out, and then, you know, write this as 3 times the limit as x approaches 1 of x squared. Figure that out. But again, you can just stick it in, right? Stick the 1 in for x. So that's just going to give you 3 minus 1 plus 5, which equals 7, right? And here's a graph of the curve. You could look at it graphically. A lot of times I'll expect you to evaluate these algebraically, and I probably won't have too many simple problems like this where you plug in there, but that would be another way you could sort of do this or double check your limit, is graph the function and see, you know, as x approaches 1, does it look like it's approaching height 7, right? I mean, I guess it does, right? Here again, you know, technically you should use the limit laws to break this apart, but because of that theorem, again, I can just, wherever I see an x, I can just put in a -1. So I'll get -1 plus 1 plus 1 plus 1 equals 2. And then just stick -1 in for x, and I'll get 2. Right, again, you can see if you graph the function, you know, that sort of corroborates what you've got there. Not all functions are going to be that easy. We'll see that for rational functions, you know, something where you've got a polynomial divided by a polynomial, you can essentially also just stick the limit in, provided that the bottom is not equal to 0. Okay? So if you have some function like this, again, you know, technically I suppose you should take the limit of the top and the bottom separately, then take the limit of each term separately. But again, because we have this result, this theorem, you can just stick 1 in for all the x's, right? So that just stick 1 in for all the x's, and you get 7/2, right? Now graphing these is going to be a little bit harder, but That would be another way you could do this or verify things, is look and see if as x approaches 1, does it look like the height of this function is approaching 7 over 2 or 3.5. Okay. Here's another example. So if you take the limit here as x approaches 0 of this, right, you just sticking 0 in for x, you get negative 7 over 3. That'd be your answer, right? Same thing for this, you just stick 1 in. Now in this case you get something kind of weird happens though, right? You get a 0 in the denominator, and that's undefined. So we'll see in some cases you can evaluate limits. In this case, in some cases you can't. It turns out that in this particular case the limit does exist or does not exist, but there will be some cases where you can find the limit, right? So sometimes limits can be evaluated numerically, just like we did, right? Just by plugging in the number or by looking at the graph, but sometimes it's better to evaluate them algebraically. And it is kind of hard to tell sometimes, you know, if you have something like this that happens, when does the limit exist and when doesn't it? And I'll, you know, hopefully by doing the homework and stuff, you'll have enough practice that should kind of give you an idea of what to do. But in general, when you're trying to evaluate a limit, plug in first and see what you get, right? If you get something that doesn't make sense or is undefined, or you get 0 divided by 0, try some sort of algebraic manipulation. And in general, most limits are very difficult to evaluate, right? So, you know, the ones we're going to study in this class will be, you know, there should be some methods similar to what we've already seen that you can use to evaluate them. So if you've done the homework and things like that, you should be in pretty good shape. You know, I should give you problems that are pretty similar to the homework. And we'll see later on, once we've learned how to calculate slope and the derivative, there will be other techniques that we can use. But obviously we don't know that yet. So here's an example of a function where something kind of weird will happen. And I should mention too that, you know, another way you could evaluate limits is just plug in values of x that are closer and closer to the limit. So in this particular case, if you plug in values of x that are closer and closer to 0, either from the left or the right, but in this case you get something kind of weird that happens. And so this is kind of where graphing calculators and technology are kind of limited. You know, most of the time if you graph a function, especially if it's nice like this, right, you can just look at it and see the limit, kind of like we did with these examples. But there will be some problems where you won't be able to do that, and you'll have to tackle these algebraically. So let me show you why this doesn't work first, right? So if I pick values closer and closer to 0, if I approach 0.01, it looks like it's settling down to a height of 0.05. But if I pick values of x that are even closer and closer to 0, it looks like this limit is approaching height 0. So what is it? Is the height 0.05 or 0.0? You might say, well, they're close enough, but again, you can't have an answer that's both 0.5, 0.05, and 0. So the question is, how do you tackle a problem like this, right? Where when you plug in the limit, you get 0 divided by 0. And we'll see that there are other ways to tackle this. But one way you can do this, and it depends on the kind of function you're dealing with, but especially problems like this where you have square roots, what you typically want to do is multiply by the conjugate. So you might remember the conjugate of an irrational expression like this is something where you change the minus to a plus. So I'm just going to multiply this expression on the top and the bottom by the conjugate of the numerator. And you might wonder, well, how can you do that? Well, you can multiply any fraction by whatever you want on the top and the bottom as long as you do the same thing, because this is just another way of writing 1, right? So I'm basically just multiplying this by 1, and then just go ahead and multiply everything out. So if I FOIL everything out on the top, right, this is the form of a minus b times a plus b, so that should give you something in the form a squared minus b squared. So maybe just to work that out more carefully here, right, if you take that times that, the square roots will cancel, right, and you'll get x squared plus 100. And then if I take this times the second term here, I'll get plus 10 times the square root of x squared plus 100. But if I take this times this, I'll get minus 10 times the square root of x squared plus 100. So the middle terms will cancel there. And then if I take negative 10 times 10, that gives me minus 100, right? So that gives me the top. And you'll notice in the next step we can cancel the 100s there. And then on the bottom, I guess I can multiply the x squared times this term and that term. I can't really put it inside the square root unless I write it as x to the 4th. So let's just leave it like that for now. So the 100s cancel, and then you notice something else nice happens here. The x squareds cancel also. Okay, and so then you'll get this, and then take the limit of this as x approaches 0. Well, as x approaches 0, this will get closer and closer to 0, so you'll get the square root of 100 which is 20. So this will wind up being 1 over 10 plus 10, which is 1 over 10, or 20, which is 0.05. So that 0.05 answer that we got before is the answer. And if you graph the function, you can see that. I don't know if we'll graph this one necessarily, but so you can see even using a computer, the computer isn't necessarily going to give you the right answer, right? But if you do an algebraic analysis like this, so if you ever see anything with a square root in it like this where you have two terms, try multiplying by the conjugate. That will usually work. Here's some other examples. So again, this one's pretty easy. This is just a polynomial. So like I said before, plug in first. If it works, that's the limit. So just plug in 2 for x. It's a polynomial, so that should just give you the answer right away. That just gives you 3, right? 2 squared plus, oh, one of these, this is supposed to be a minus here, I'm sorry. So, 4 plus 2 minus 3, right, that does give you 6. Now, for something like this, when you plug in the limit, I guess you could try to factor the bottom here. You'll notice that those cancel, right? Because I think if you plug in the limit in this form, you get 0 divided by 0, kind of like we did for this one. So if you ever see anything like that, try factoring the bottom. Then you can cancel those terms, as long as the limit isn't approaching that. And so you'll get this. So in other words, this will basically be the same graph as this, except you'll have a hole in it at x is equal to -3 here. And I guess the limit is approaching that, right? So again, they may not be, -3 might not be in the domain here, but it should basically approach the same height, right? So remember, the function doesn't have to be defined at the limit in order for the limit to exist. And again, you could try graphing this one and see if, as x approaches -3, does the height approach -1/2 there. Now, in a graphing calculator, you're not going to see the hole here, but this is basically going to look like the graph of 1 over x shifted 1 to the left. So it should look something kind of like this. So you can see that as x approaches -3 over here somewhere, right, I guess I haven't drawn this very well, -3 over here, the height of the function should approach -1/2. Here's one with the square root in it again. So again, don't automatically multiply by the conjugate. Plug in first and see what you get, right? But in this case, if you plug in, you get -2 plus 2, which is 0. Here you'll get -2 squared, which is 4. 4 plus 5 is 9. Square root of 9 is 3. 3 minus 3 is 0. So you get 0 over 0 again here when you plug in. So again, since we have a square root in it here, try multiplying by the conjugate. Try that trick like we did in this one, right? And I heard somebody say before that in math, a technique is a trick that you've seen more than once. So I'll call this a technique now. But if you see something in there where you've got a square root in it and it doesn't work out, try to plug in here first. I could try to trick you and give you the limit as x approaches 0, in which case you would get a limit. It would just be 2 over square root of 5 minus 3. But in this case, because you do get 0 over 0, you want to multiply by the conjugate. So on the bottom, again, I'll have something in the form of a minus b times a plus b. So I'll just get a squared, which will wipe out the square root, minus 9. And then on the top, I'll just get that times that. Let's just leave it like that for now. We could FOIL this out, but I think you'll see something nice will happen here. So if I simplify the bottom, I get x squared minus 4. Now I can factor this, right, into x minus 2 and x plus 2. And luckily, that allows us to cancel the x plus 2's there. And if you think about it, that was the thing that was causing the problem, because when I plug in -2 there and -2 there, I get 0 divided by 0. So let's plug in here and see what we get. So if I do that, I'll get what? 4 plus 5, so that'll be 9. So square root of 9 is 3, so I'll get 3 plus 3 or 6 on the top. And I'll get -2 minus 2 on the bottom, which will be -3 over 2, right? And so that will give you a value of -3 over 2. Okay, so a lot of the problems in the homework you should be able to handle using these methods. So, try these. If you guys do want extra homework problems to do, the UW does have a free online book, I think. Just do a search for free online UW-Madison Calc book. And there will be more problems in there if you want. I think they do have answers in the back. But again, we're not really following that book, so the sections might be kind of out of order there. Okay, so let's look at another important result. So it will turn out that not every limit can be resolved this way, so we will have some other techniques. Another technique that we'll use is something called the sandwich theorem, and this is sometimes called the squeeze or pinch theorems. And basically, I kind of try the other methods first, just try plugging in and then maybe try factoring or dealing with the square roots by multiplying by the conjugate. If that doesn't work, think of the sandwich theorem or squeeze theorem as sort of a secret weapon you can use as sort of a last resort. And sometimes it'll work and sometimes it won't. But if you can't think of anything else to do, try the sandwich theorem. But basically what the sandwich theorem says is, suppose you've got some function f of x that's sort of sandwiched between h of x and g of x. So that's why it's called the sandwich theorem. Think of these two things as the bread, and this is the meat of the sandwich. In other words, f of x is always trapped between the function h of x and g of x, right? So you've got your function h of x going along here, and your function g of x going along here. And if there's some point where these two functions approach the same height, then the function f of x that's always trapped between them also has to go through that point as well. So what it's saying here is if there's any place where the upper function and the lower function, the bread in other words, approach the same height, then that forces the meat of the sandwich to also approach the same height, or sort of be squeezed into the same height there, right? So here's a much better drawing than the crude drawing I just did. So let's say you've got some function h of x and some function g of x, and at some point c, h of x and g of x approach the same height, and the function f is always sandwiched or trapped between those two, then the function f has no choice but to go through the same height as well. And we're not going to formally prove this result. If you look in the back of the textbook, there are proofs of all these results, but they involve some techniques that we'll get to. They involve something called epsilon delta proofs, which we'll touch on briefly, but I don't know if we'll emphasize that much. And like I said, there are other approaches to dealing with these limit problems other than the epsilon delta approach. The epsilon delta approach is sort of a standard approach, but there are non-standard techniques, but they're not usually used all that much. So if you go on and take more math, your professor probably won't use the non-standard techniques, but they are available. If you're interested in that sort of stuff, you can do a search for non-standard analysis, but then you're kind of getting into the nuts and bolts and the guts of calculus, and we're just basically kind of learning how to calculate. So we're basically just kind of learning how to drive the car. We're not learning how to build the car or work on the engine. If you really want to understand how calculus really works and understand the proofs, you have to take an analysis class where you'll do more epsilon delta proofs, or if it's a non-standard class, you'll talk about non-standard techniques. But so let's look at a specific example. So let's say I have some function u of x, we don't know what it is, but it's always sandwiched between this parabola 1 plus x squared over 2 and this other parabola 1 minus x squared over 4, and we want to know what is the limit of this function u as x approaches 0. Well, again, you can just look at the graphs and see, well, it looks like these two are approaching height 1, so that should also approach height 1 also. Now, these problems can get to be a little bit tricky if you're not given the upper and lower function. We'll maybe look at one of those, but here, let's look at some more examples. So here's the function, the absolute value of x, or absolute value of theta. Here's negative absolute value of theta. Sine is always trapped between those two. So as x approaches 0, the height of sine of x should also approach 0. I guess we kind of already knew that anyway without the sandwich theorem. Here's another function here, 1 minus cosine of x, or 1 minus cosine theta. And we're asking what's the value of 1 minus cosine theta as x approaches, or theta approaches 0. Well, in this case, you could probably do this pretty easily without the sandwich theorem, right? I mean, what's cosine of 0? Well, that would be 1, so you basically get 1 minus 1 or 0. But you can also try to sandwich this between two functions, like here we're sandwiching it between the absolute value of x, or the absolute value of theta, and just the constant function 1 here, right? And so again, this function and this function will approach height 0 as x approaches 0. So again, these are two examples are kind of silly, right? Because you could sort of figure out the limit of sine of theta and 1 minus cosine theta without the sandwich theorem. But here's some examples. So here's another example. This one's a little bit tricky because I'm not giving you the functions to sandwich this between. So you have to kind of think about what are the two functions you could sandwich this between? And then also remember that the two functions have to approach the same height as x approaches 0. And there's a couple different ways you can approach this. One way you can do this is just sort of play around with stuff, and I'll try to give you something that's pretty obvious. But you can also kind of start with what you know. You know, if you think about this, you know, no matter what 1 over x is, remember cosine always has to be between 1 and -1. So you could kind of start out with that. And then, you know, I want an x squared, so let's try multiplying everything by x squared. And you might worry about having to flip the direction of the arrows because I'm multiplying by something, but if you think about it, x squared is always positive, right? So I get that. Well, lo and behold, this is the limit of the function we're looking for. So let's ask ourselves, well, what's the limit as x approaches 0 of this function? Well, that's 0, right? What's the limit as x approaches 0 of this function? Well, that's also 0. So these two functions approach the same height, right? We could even draw a rough sketch here, right? This is just a parabola that opens downward, right? The minus x squared and the positive x squared. Who knows what this function even looks like? It's, you know, it's a trig function, so it's probably wiggling around in here. You could graph it if you wanted to, but since these two functions approach height 0 as x approaches 0, that forces this function, whatever it is, to also be 0, right? So the limit of that will be 0. So again, the sandwich theorem can be kind of hard to use. You know, if you just try plugging in 0 for x, that won't always work either, because you might say, well, you know, this is going to be non-zero and this will be 0, so you should always get 0, but, you know, that's kind of informal. You know, I will allow you to sort of reason informally on the exam, provided you get the right answer, but I would really rather have you invoke some theorem or something like that. But I might at least give you partial credit if you can sort of guess the limit or give me sort of a verbal argument there. And there might be other ways to prove this as well. We'll see later on that there might be other ways to prove the limit here. But so here's a much better picture than the one I drew by hand, right? So here's x squared minus x squared, and as x approaches 0, the height of that will be 0. All right, well, that brings us to the last theorem here in this section and the last slide here. And this says that if f of x is some function where the height of f of x is always less than g of x for all x in some open interval around c, so you've got c here and you've got some open interval around it, and f of x is always below g of x. Maybe f of x could be equal to g of x, but it certainly can't be bigger. And the limits of f and g both exist as x approaches c, then basically what this is saying is it's saying the height that c approaches in f of x, the height that f of x approaches as x approaches c, should be less than or equal to the height that g of x approaches. And again, we aren't going to go through a formal proof of this. If you want to look in the back of the book, I think there is a formal proof of this theorem, but it's kind of common sense if you think about it, right? If this function is always below this one on this interval, then the height of this function has to always be less than or equal to. Maybe it's equal to if the function f of x comes up and touches this one, but it's certainly always going to be less than or equal to that if f of x can never be above g of x. Okay, so this might be another theorem that you might use. Doesn't really tell you what the limit is, it just tells you that the limit exists. So not an especially useful theorem, but maybe you want to actually know that the limit exists before you go looking for it. If maybe you can find the limit of this function. If this limit exists, then at least you'll know that this limit exists and that you're not going on some wild goose chase. So that's the basics of limits. We'll do some more advanced things later on. But that should hopefully give you guys a basic idea there. So if you have questions or anything about that, and I know we are getting into more difficult material, make sure you let me know. Right, bye.